أعزائي طلبة وطالبات الصف الثالث الثانوي القسم العلمي رياضيات لغات، أهلا بكم في حلقة جديدة من حلقات برنامجنا برنامج داينامكس. النهاردة إن شاء الله هنستعرض بعض المواضيع المهمة الأساسيات اللي لازم نكون عارفينها. هنتعرف على معنى الماس، هنتعرف على اليونتس بتاعت الماس، هنتعرف على مومنتم، نتعرف على نيوتن لوز، فيرست لو، سكند لو اند ثيرد لو، ونشوف ازاي نقدر اكزامبلز على النيوتنز لو، وده حاجة مهمة جدا في منهجنا السنة دي. Dear students of grade 3 secondary, welcome to our math program. Today we have dynamics. Our lesson today is Newton's laws of motion. Let's start with the mass. The mass m of a body is a positive scalar quantity which is proportional with the weight of this body. And we can use the unit of mass 1 ton, which equals 1000 kilogram. 1 kilogram equals 1000 gram, and 1 gram equals 1000 milligram. We have momentum. The momentum vector of a particle at a certain instant is defined as the product of the mass of the particle and its velocity vector at this instant. We have a body of mass m and its velocity vector v, then the momentum vector or vector h equals the product of the mass of the body multiply its position or the vector velocity of this body. And the algebraic measure of the momentum vector is equal to the product of the mass times the algebraic measure of the velocity of the body at this instant. What about the unit of measure of the magnitude of momentum? Momentum h equals the product of m, mass, and velocity v. So we can use mass unit multiply velocity unit to find unit of the momentum h. So we can use gram centimeter per second, kilogram meter per second, and kilogram meter per hour. Let's start with the first example. Calculate the momentum of a train whose mass is 40 tons moving towards the north with uniform speed of magnitude 72 kilometer per hour. The mass equals 40 ton and the velocity 72 kilometer per hour. The momentum h equals m multiply v. M equals 40 and the velocity v equals 72, so h equals 40 multiply 72. 40 multiply 72 equals 2880 ton times kilometer per hour, because we find the momentum h by product 40 ton multiply 72 kilometer per hour. Then the result h equals 2880 tons kilometer per hour. Now we move to the next example. A car of mass 2 tons moves in a straight line such that the position vector x equals 3t power 2 minus 4t plus 1 in the direction of the unit vector E, where E is the unit vector in the direction of motion of the car. If x is the algebraic measure of the position is measured in meter, find the magnitude of the momentum of the car when it starts to move, then after 3 seconds of its motion. We have a relation between vector x and time t. Vector x equal 3t power 2 minus 4t plus 1 e, where vector e is the unit vector in the direction of the motion of the car. we can get the velocity vector. Velocity vector equal the rate of change of position vector with respect to time, or vector v equals derivative of vector x with respect to respect to the time t. Vector equals derivative of 3t power 2 is 6t minus derivative of 4t equals 4, and 1 is a constant. The derivative of the constant equals 0. So vector v equals 6t minus 4 in the direction of unit. The first required at the beginning of the motion. At the beginning of the motion means the time equals what? Equals 0. So the velocity equals 6 times 0 minus 4 in the direction of E. Then vector v equals negative 4 in the direction of vector E. Now, what about vector h? Vector h equals the mass of the car multiply velocity vector v. Vector h equals the mass equals 2 tons or 2000 kilogram multiply vector v, which is negative 4 vector e. 4000 multiply negative 4 equals negative 8000 e, and the magnitude of momentum equals, in this case, equals 8000 kilogram times meter per second, because the mass in kilogram and the velocity in meter per second unit. What about the second required? The second required when the time equals 3 seconds. The velocity at t equals 3, vector v equals 6 multiply 3 minus 4. 6 multiply 3, 18 minus 4. Then velocity vector equals et minus 4, 14 in the direction of unit vector e. Now, what is the momentum vector at this instant? Vector h equals m multiply vector v. Vector h equals 2000 times 14e is 28,000 in the direction of unit vector e. So the magnitude of the momentum in this instant equals what? Equals 28,000 kilometer per second. Dear students, we have a very important concept, the concept of the change in momentum. The change in momentum equals vector h2 minus vector h1. Vector h2, the momentum of a particle at an instant, minus vector h1, the vector of momentum at a previous moment. So h2 vector minus h1 vector equals m vector v2 minus m vector v1. We can take the mass m as a common factor, so the change in momentum equals m multiply vector v2 minus vector v1. The symbol delta h means that change in momentum equals m multiply delta v, or vector delta vector h equals m multiply vector v2 minus v1. And we have a very important note. Dear student, determine the sign of the algebraic measure of each velocity before and after change, and the magnitude of the change in momentum equals norm vector h2 minus norm minus vector h1. Norm vector h2 minus vector h1. Now we move to the next example. A rubber ball of mass 200 grams is let to fall on a horizontal surface from a height of 90 centimeter to rebound up to a height of 40 centimeter. Calculate using kilogram meter per second unit the magnitude of the change of momentum of the ball as a result of impact. First, let vector C, be the unit vector directed vertically upwards, studying the motion of the ball in case of falling. We have initial velocity equals 0 and S 90 meter and the gravity 980 centimeter per second squared. So the relation between the velocity and displacement is v squared equals v naught squared plus 2gs. What is the velocity when the ball reaches the ground? V squared equals initial velocity 0 because the rubber ball is let to fall, meaning the initial velocity equals 0, plus 2 multiply g 980 centimeter per second square, multiply the displacement or the height, which is 90 centimeter. So the velocity equals, v equals 420 centimeter per second. The velocity before the ball reaches the ground equals 420 centimeter per second, and this velocity in the positive direction of motion, so the velocity v1 equals 420 c. C is a unit vector in the positive direction of the motion. Now, studying the motion of the ball in case of rebounding. What is the relation between the velocity and displacement? V equals v naught squared plus 2gs. In this case, the ball reaches the maximum height, then the velocity equals 0. And the initial velocity or the velocity of the rebounded v naught is unknown. Minus 2 times 980 centimeter per second squared. Negative because the motion in this case upward. Upward is in the negative direction, so the direction of g is negative. And we can substitute by negative 980 centimeter per second. Multiply s in centimeter, the maximum height, so we can find the velocity of the body in case of rebound, which is 980 centimeter per second. Now we have v2 vector equals 280 c in negative direction of the motion. Now the change in momentum, delta h vector equals m vector v2 minus vector v1. Delta h equals the mass 200 gram. 200 divide 1000, then the mass in this in kilogram. What about the velocity? Velocity vector v2 equals negative 280 centimeter per second, divide by 100. The velocity vector velocity v2 equals negative 2.8 in meter per second, minus 4.2, which is 420 divided 100, equals 4.2 meter per second in the direction of the unit vector c. Then delta h equals negative 1.4 in the direction of unit vector c. Then the magnitude of the change in momentum equals 1.4 kilogram meter per second. Dear student, now we have Newton's first law. Everybody perseveres in its state of rest or of moving uniformly unless acted upon by an unbalanced external force, by an external effect. What is uniform motion and rest? Newton's first law considers the two states of rest and uniform motion in an equivalent situations, where the resultant of the acting forces is equal 0 in two cases. In this case of rest or uniform motion, the algebraic sum of the components of the acting forces in two perpendicular directions must vanish. means equal 0. Now let us discuss the concept of uniform motion of a body. Uniform motion on a horizontal plane under the action of a horizontal force. We have a of weight W moves on a horizontal road. We have a normal reaction N perpendicular to the plane, and a force acting on the body F to move it, and a resistance force R in the opposite direction of the motion. So we have two equations. The first equation, the weight W equals the normal reaction N, and the force F equals the resistance force R. Uniform motion on a horizontal plane under the action of an inclined force. We have force F inclined to the horizontal, or inclined to the by an angle of measure theta. We can resolve this force in two perpendicular directions. Two components. The first component F cosine theta parallel to the plane of motion, and the other force F is F sine theta perpendicular to the plane of the motion, and we get the two equations. N plus F sine theta equals W, and F cosine theta equals R. F cosine theta equals R, meaning the resultant equals 0, and N plus F sine theta equals W means the resultant of the forces equals 0. What about vertical uniform motion? When the body moves in the vertical uniform motion, we have direction of uniform motion downwards. So the resistance force in the opposite direction of motion upwards, and R in this case equals W. R is the resistance and W is the weight. What about the inclined plane? Uniform motion on an inclined plane. We have a body of weight W moves on an inclined plane, inclined to the horizontal by an angle of measure theta. The direction of motion is parallel to the line of the greatest slope of the plane upwards, and the body moves with a force F. The resistance force R in the opposite direction of the motion, parallel to the plane of the motion downward, and we can resolve the weight force W in two perpendicular components. The first component W sine theta parallel to the line of the greatest slope downwards, and W cosine theta perpendicular to the plane of the motion downward. From the opposite figure, we can get the two equations. The first equation, F equals R plus W sine theta, and the second equation, N equals W cosine theta. The force F may make an angle alpha with the plane, with the inclined plane. We resolve this force in two perpendicular components. One of them, F cosine alpha, parallel to the line of the greatest slope upwards, and the other is F sine alpha, perpendicular to the plane of upwards. If the direction of motion upwards, then the resistance force in the opposite direction of motion, so are parallel to the line of the greatest slope downwards, and we get the two equations. F sine alpha equals R plus W sine theta, and N plus F sine alpha equals W cosine theta. Maybe the force acts in the direction of the line of the greatest slope downward. In this case, the direction of motion downward. And the two equations are r equals f plus w sine theta, and n equals w cosine theta. The last case, if the body moves without force under the action of its weight only, then the resistance in the direction of the line of the great slope upwards or in the opposite direction of the motion. And we have the two equations, r equals w sine theta and n equals w cosine theta. Example, a particle moves in a straight line such that the algebraic measure of its velocity v is given as a function in time t with the relation v equals 6t power 2 minus 24, where the velocity v is measured in meter per second. The first required, find the magnitude of the acceleration of the particle when its velocity becomes 30 meters per second. The second required, find the magnitude of the displacement during the time interval t belongs to those interval 1 and 4. Now we have velocity v equals 6t power 2 minus 24, the relation between velocity and time. We can get the acceleration by a equals dv dt, the derivative of velocity with respect to time, equals 12t, then the acceleration equals 12t. What is the magnitude of the acceleration when the velocity equals 30 meters per second? When v equals 30 meters per second, 6t power 2 minus 24 equals 30. 6t power 2 equals 54 divided 6, then t power 2 equals 9, and time equals root 9 equals 3, and the acceleration a equals 12 multiplied 3 equals 36 meters per second squared. T belongs to 1 and 4, close the interval. V equals 6t power 2 minus 24. And we know that the velocity v equals the rate of change of position x with respect to time. So dx dt equals 6t power 2 minus 24. We can separate the variables. In the left side, definite integral of dx from x node to x equals definite integral of 6t power 2 minus 24 dt from 1 to 4. The definite integral of the left-hand side is x from x node to x, and the definite of 6t power 2 minus 24 with respect to the time t is 2t power 3 minus 24t from 1 to 4. The left-hand side, x minus x node, and the right-hand side is 54 meter. Then s equals 54 meter. Now we have Newton's second law. Rate of change of momentum with respect to the time is proportional to the acting force and takes place in the same direction in which the force is acting. The mathematical expression of Newton's second law. The rate of change of momentum, the derivative of h with respect to time, varies as vector f. The derivative of m multiply vector v with respect to time varies as vector f, and the derivative of m multiply vector v with respect to time equals constant k, the constant multiply vector f. K is the constant, and this constant equals 1. If m is a constant during the motion, then the derivative of v with respect to t multiply m is a constant, equals kf, and the derivative of velocity is the acceleration, so m multiply vector a equals k multiply vector f. in their direction by means of their measures as f vector equal fc and a vector equal ac, where f and a are the algebraic measure of the two vectors, vector f and vector a, and they are positive. Dear students, by this example we come to the end of our program today.